All right, I gave you back your exams. If you have any questions on the exam, please feel free to come talk to me. The calculus specific problem on the exam was one where you were to determine if it was conservative, and if so, what the potential energy was for that force. Well, the first step to determining if it is conservative is to calculate the curl. And so if you calculate the curl, you should have found that the curl was not zero, hence not conservative, hence problem over. Okay, today we're going to talk about the center of mass and moment of inertia. Now, these are things that we've talked about in the other class, very briefly actually. And here we're going to talk about them more extensively. In fact, there's a reasonably large chance that it will be one of these two things that you will see for your calculus question on the next exam. So let's get to it. In Physics 151, we learned that the center of mass was the average position of mass. So if we have three pieces, we just take the position of each piece times the mass of that piece, divided by the total mass. Or moment of inertia, we learned, was mass times radius squared. If we have more than one mass, we have to take each mass times its radius squared and add them up. Those work fine if we have discrete objects. But if we have a continuous object, like this, the continuous object has mass everywhere. You can't just add up each piece of mass, you have to integrate. And so those equations won't work for us if we're working with a real object. So we do the equivalent of adding for calculus. That is when you have a continuous material, instead of having summation, it becomes integral. And as I think I was pointing out to Nathan, sigma is S in Greek. And the integral sign is just an elongated S. And that's because they both mean to sum things up. The difference is just sigma is for discrete things, and the integral is for continuous things. Now we had sum of x times m over sum of m. That was the center of mass. So we replace the sigma with an integral sign. That's easy. But then we have to have something we're integrating with respect to. Right? Integrals don't just come by themselves. You have to integrate with respect to a variable. And so one might look at this and say, well, I have two variables, position and mass. So how do I know if I'm integrating over position or over mass? We have mass continuously distributed in space, but it's continuous distance, right? So we can integrate over the entire region. Well, the way this works out, and I really in my head can't distinguish why we do x dm rather than m dx. It probably would be 6 1/2 dozen the other, is the mass at some point is so small that we call it dm. It's a little tiny piece of mass. And so this dm is the same as this mass, but it's a very tiny piece of mass instead of a discrete piece of mass. And then the space will be continuous. So we have to determine what dm will be based on our actual system. And then we're just going to do integrals. Now I'm going to do examples of these. So this is just introducing the equations. Then we do examples. It'll make a lot more sense than just looking at an equation. If we're doing moment of inertia, it's basically the same thing. It's integral of r squared dm. Notice I put a little perpendicular sign there. Moment of inertia, the r, is the radius from the axis of rotation to where the mass is. It's not the radius from a point to where the mass is, but from an axis of rotation to where the mass is. So that's why we have the perpendicular, and it's going to be important. I put here where dm is equal to rho dv. This is for 3 dimensions. So we have begging the question, what is rho? Rho is defined as mass over volume, the density. So if I take, once again, I'm going to take this away from Nathan. If I take this, this is uniform. And by uniform, we mean the mass per volume is the same in any part of the sphere. Okay, ignoring that it's hollowed out in a few places. And so rho would just be a constant. I would take the volume of the sphere, 4/3 pi r cubed, and the mass of the sphere, and divide the mass over volume, and that would give me the density. It's possible, like with the Earth, to have density change with radius. And then that density becomes a function, making our calculus more interesting. And by interesting, I do mean difficult. So we have to worry about what is the density of the object, is it changing? And then I have dV. I know the three of you in calculus have done some of this in the near past, not chapter 8. Wasn't chapter 8 a pain? You know, yeah, I know. You're like, no, it was fine. If you guys need help with the calculus, I've been doing all of the calculus you've been doing. So, you can come from me for help with calculus too.
So that'd be a little odd.
No.
You got a calculus teacher. You have physics students.
Yes, but you're my physics students. And we're using calculus in physics class. It's something you have to be able to do. And what?
He knows what he's doing.
Yeah.
I don't want to get valuable time from other students. That's all it is.
As Nathan asked me yesterday, do students ever come to help with physics? Because it's not very often. You don't have to worry.
Okay. I enjoyed chapter 8, by the way.
You enjoyed?
Yeah.
Oh boy.
The punishment's just fun.
Okay. The punishment was fun. I see where you're coming from now. That the
Satisfying to do it
once you're done. The trig substitutions were my least favorite thing in calculus.
Well, yeah, those. But, it's all
Okay.
simple.
So dV, d volume, that's a three-dimensional d. Right? That's going to be a dx, dy, dz if you're in Cartesian coordinates. Triple integrals are not as fun as a single integral. And so one way, if you have appropriate symmetry, is you might be able to say dV is the area times dx. I know you've done that, I think it was chapter 6 or chapter 7 in your calculus, where you calculated the volume by using area times dx. And so we'll still have the same dV idea as area dx. We'll just have times rho for dm, and then times r squared to make life just a little more interesting. So that is the basis of what we're going to be doing today. Right now, you probably have no idea how to apply any of this. So let's apply something in the simplest case. I have a uniform rod, and the mass is evenly distributed throughout the rod. What does it mean to say that the mass is evenly distributed? The density is a constant function. And so the density is equal to the mass over volume is equal to constant. Now, for a rod of negligible radius, we'll treat it as a one-dimensional object. Obviously, a real rod is three-dimensional. But if it has a small radius, we'll say we can treat this as a one-dimensional object. And so we'll just take the cross-sectional area. So if I have a rod, the cross-section, okay, to be consistent, I should make it look like this. The area of the end is the cross-sectional area. Thank you for that help. Area is pi r squared for the rod. And we'll just say, okay, the area is small enough that I will just say it's one-dimensional. And so my density times area is going to be the actual mass per unit length. And we'll call the mass per unit length sigma. And so then we'll put dm is equal to sigma dx. Or not sigma. That's lambda. I said sigma twice. Lambda dx. So that's just